Season അനുസരിച്ചാ സമയം 1500
போயிட்டு அவங்களுக்கு பொருள் Hi everyone. Hello.
Hello. Hi, sir.
Yes, sir.
Hi.
Good evening.
I hope all of you can hear me.
Yes.
Yes, yes.
Okay.
Yes, yes.
Yes, sir.
Okay. Okay. Wait. Hold on. Okay. Good evening, everyone. My name is Sarath, and I will be taking the subject introduction to heat engines. Actually, so today it will be the first day of the class. So today we will first go through some of the basic uh, concepts of heat engines. Then in the further classes, we'll move on to different types of engines, their working, as well as fuels, and how the combustion happens within the engine, and so on. Okay, so today we will understand the basic principles of heat engine. Okay, so these are the contents that we are going to discuss today. Hope I think you are all not basically from the mechanical side. So I would like to have this introduction class so that at least there is a basic concept that you will gain before we go further into the uh, working principles or the um, principles of working of the engines. So today we will be discussing about the definition of heat engine. What is a heat engine actually? The basic very basic thermodynamic principles behind that, and classification of heat engine. We are not going deep into the classification, the basic difference, how many types are there. I mean the conventional ones, currently running ones. So next one is the historic evaluation. We are not going too deep into that. Just we will be discussing the milestones of the evolution of these engines, and we have a few laws of thermodynamics that also we are not going too much deep, but basic idea is required for understanding the working of a heat engine. So let's move into that. So what is a heat engine actually? So as the basic principle, thermodynamically, heat engine is a device, any device that can convert thermal energy into mechanical energy. Hope we know what is a thermal energy and also what is a mechanical energy. So thermal energy, we can say it as a heat, and mechanical energy, we can refer it to as work, mechanical work. Okay, so I have highlighted those heat and work um, in red colors, because we need to correctly understand. I mean, we need to understand properly before moving to that contents. Okay, so we will be having a concept of heat as well as work. That itself is a thing, but a little more. I mean, a little more additionally, we have to know about that. So, as per the definition, or as per this definition, that means any device that can convert thermal energy to mechanical energy is considered to be a heat engine. Then the crackers, we used to provide crackers, right, which moves up and it will crack above in the sky. Rockets, cracker rockets. That also, by this definition, it is also a heat engine, right? Rocket engines, maybe guns. That all comes under the heat engine by this definition. So what is so whatever we know is far different from this propel. I mean, these bodies that is converting thermal energy into heat energy, right? So there is a difference. So for understanding those, we have to go through these basics. So here what I have listed is steam engine, gas turbine, petrol or diesel engines that we usually see now. So what I have highlighted is again listed here. So we know what is an energy. Energy is the we all, as we all know, energy is defined as a capacity to do work. Simply, we have defined it in +2 classes, right? But in thermodynamics, energy is defined as the same way only it is being defined, but it is classified only as two. One is a stored energy and one is the energy in transient. Okay, in stored energy and energy in transient. And within that also classification is very basic. That is stored energy is the total internal energy. Total internal energy. Okay. And stored energy means energy that is being stored in the body. That means, I mean, the total internal energy includes a lot of other energies like chemical energy, nuclear energy. Maybe you have you will be knowing, right? We have experienced how much energy is there in the body or atom of a uranium 235, right? It was explored in Hiroshima and Nagasaki. It was not a kilometer long bomb that was dropped there. It was carried in a plane and was dropped there. It still created a large devastation. I mean, the destruction, that kilometers were destroyed. That's just the energy stored in an atom. I mean, molecule of uranium 235. A few molecules were used, right? That we know. So that much energy that we cannot calculate, but we can know the difference in a process. The change in internal energy in a process that we can find out. That means if a body exists in some kind of internal energy, total internal energy, and some process happened, some energy is being transferred into the system, I mean into the body, then the energy of the system has increased, and we can say we can find that change in total internal energy. That is what it is being supplied, right? The energy that is being supplied is the difference between the stored energy levels. Hope you understood. So that is the total energy. And coming to the energy in transient means the energy being transferred between two bodies because of a potential difference. It may be a temperature difference, it may be a height difference, it may be some other difference. Anyhow, the energy transferred between two bodies due to a potential difference is known as energy in transient, and that is also divided only into basically into two, that is heat and work. Not much, we all know, right? A lot of energies we know, but it is basically divided into heat and work. So here it is the importance what is happening in an engine. This part is very important in a heat engine. So I will tell you what. Again, energy in transient is only heat and work. So heat, what is a heat? We all know it is a form of energy, but how it is different, how it flows, I already told that heat is energy in transient. So how heat flows from a body to the other body, how it flows, flows because of the temperature difference. So heat is a form of energy. You have to remember nicely, because in coming sessions it is a very simple concept, but in the coming sessions you won't that won't come into your mind. So that's why I'm telling you that this total energy is the stored energy, and energy in transient is of two types only, that is heat and work. Heat is the form of energy in transient, that is one form of energy that is transferred from one body to the other by virtue of the temperature difference. Okay, by the virtue of its temperature difference. So what is work? So every energy in transient, whatever energy is there which is in transient. Hello, okay, hope you can see the PPT, right? You can see the PPT. Hello.
Yes, sir. Yes, sir.
Oh, okay. So all the other kind of energy in transient other than the heat transfer or other than the virtue of temperature difference is termed as work. All the other energy transfer other than heat is known as the work. Okay. Okay. So this includes electrical energy. This includes magnetic energy. This includes mechanical energy. I mean, everything will be coming under the work. But for us, for who is going to study about the heat engines, work actually means mechanical energy only. So for us, for the convenience of us, for our convenience, I mean our convenience, will be terming energy in transient as heat and mechanical work. Okay, so that's what I was referring to here: heat and mechanical energy, thermal energy and mechanical energy, heat and work. But there are other kinds of works also. That is, as I told you, maybe there are electrical energy. That is, for example, when you are connecting bulb or a resistor into an electrical circuit, it raises the temperature, right? That is because of the electrical work done on that system. It's not because of the temperature difference. There was initially no temperature difference, right? When the circuit, when the current passes through that resistor or a light, it heats up just because of the electrical work that is being done there. So that is not important in case of a heat engine. So we will be considering heat and mechanical work only. Okay. So the types of heat engines, as I told you, uh, uh, by the definition, anything that converts the heat into work, mechanical work, it can be um, defined as a heat engine, right? But for us, for the conventional engines like a petrol engine or a diesel engine or a gas turbine or a steam turbine, uh, uh, there is difference from these kind of. It's different from a gun. It's also different from a rocket cracker, right? It's very different. How it is different? Because once this cracker or a gun is shot, a process happens, that is a burning happens. That means the gunpowder burns, there a heat is created, I mean a heat transfer is created, and it is converted to mechanical energy, and the process stops there. It won't generate again. I mean the temperature, I mean the heat energy is not transferred again in that system, or is being converted to mechanical energy in the system, right? It's a one time process. Once the gun is shot, I mean a gun is fired, that is done. But in case of the heat engines, I mean what we are going to discuss there, what happens is that the operation will be cyclic. That means we know, right? We will be having petrol engines, diesel engines, and how it works actually. We'll be pouring the fuel into that. That will be burning continuously and giving out the work output continuously, right? Until we switch on or switch off that one, it will work continuously. Or we can say it is operating in a cycle, or the system restores. Even though this is an example, I haven't taught you, but you can see this is happening a cyclic process. Fuel is being supplied, where it is compressed. Here you can say burning and exhaust. So the four process is done in the system. Again, it repeats. right? You can see that. So that's what we are going to study. So those heat engines that is operating in a cycle, that we are going to discuss here. So it is basically divided into internal combustion engines and external combustion engines. As the name suggests itself, internal combustion engines are engines where the combustion for producing the work done is done within the heat engine itself. I mean, the combustion happens within the engine. Here, see, this is the engine. Hope you can see my pointer. Here you can see this is one type of internal combustion engine. It's a diesel engine actually. It's a 4-stroke diesel engine actually. Here, what within the system? This is a engine within the system. What is happening within this engine? What is happening? The burning is happening. So the heat is produced here. I mean, from the fuel, heat is produced by combustion and is transferred to the piston here, where it is that heat energy is converted to mechanical energy by rotating here. Okay, rotation of the crankshaft. That is what is happening here. Okay, similar to that, there's an external combustion engine. External combustion engines are engines where the combustion or the heat is produced outside the engine. That means the heat required to run the engine will be produced. I mean, that heat source will be outside the engine. For example, a steam engine, for example, or a steam turbine, you can say. So, for example, here you can see this is a combustion chamber where it is being coal or solid fuel is burned, which creates heat, boiling water here. And this water, this is just a representation only. So this is not part of the engine. This is the engine actually. Here in the combustion chamber, the burning happens, the water will be boiling and the steam will be moving to the engine. This will be the engine part. So that high pressure, high temperature, hot um, steam will be pushing the piston and it will be converting into this heat here will be pushing this piston here. I mean, the heat here produced here will be converted to mechanical energy here. I mean, work here. Okay, hope you that. For example, I have shown here one locomotive with a steam engine, where you can see there a yellow chamber here. You can see a yellow chamber here. This is a combustion chamber where we will use coal or we will supply coal continuously, which will be burnt, and when burning, what happens? Heat will be released, and this that heat is being carried by the exhaust gases. After burning, there will be gases, right? There is a smoke which is being created that carries a heat energy, and it will be moved through a numerous pipes into the boiler. This red color is shown as the tube. It's only shown tubes, just a representation. It will be moved through a number of tubes actually, and from that tubes, heat will be transferred to the water that being stored in this boiler. And this boiler, what happens when heat is applied, this water will be converted to steam, and this steam is being transferred to the engine. Here is the engine part. Here is the engine part where it is used to move the piston. The steam comes here and used to move a piston, and that way it will be converted to mechanical energy. So it's connected to the wheels, and the wheels will be running. Hope you understood. So that is the difference. That is the internal combustion engine and the external combustion engine. So next we will be looking to the historic evolution of heat engines. Hold on a second. So the historic evolution of a heat engines, as the definition, I already told you, whatever that converts the steam into mechanical energy, it is a heat engine. So prehistorically itself, that is maybe BC 50s itself, there are systems that converts mechanical steam energy to not the steam energy, heat energy to mechanical energy. There are the histories where Chinese were fighting with the Mongols, where in 50 BC or 53 BC, where they were using projectiles like arrows that is burned using some powders, like the gun powders, not the real gun powders, but somewhat like the gun powders, so that these projectiles will move like a gun, shot from a gun. It will be moving towards the enemies against the Mongols. Like that, that here there what is happening, the while burning the powder, heat is generated and it will be transferred to the arrows, where arrows is moving. Once a body is moving, we can say it is a mechanical energy. So like that it was created, and a lot of inventions were there. Alexandria, where steam was used to rotate. For cooking also, that grilled chicken, making how to make the grilled chicken and all, where slides are used to the steam is used to run that one. Like that, now so many inventions were there before 17th century. So I have included a few listed here, not that important, but just want to show how vigorous the inventions were in the 18th century and after the 18th century. So I have listed, I have some highlighted some of the important inventions, like James Watt's. What did he invented? The steam engine. Before that also there were steam engines, but were very less efficient, cannot be produced commercially. That was not capable of producing the required amount of works. So there were other designs. There are a lot of designs actually, but James Watt, he came up with the Watt steam engine, which started the industrial revolution. That was the base thing. What the industrial revolution started, that is the growth of the industries started manifold because of the transport facilities for transportation due to the locomotive. So then after that also many inventions happened. In 1791, John Barber came up with the idea of gas turbine. Gas turbines are the basic working things, right? Abrams tanks and all. American tanks are being powered by gas engines. There are gas engines that powers aircrafts also. So that is another important invention. So in 1816, Robert Stirling invented Stirling engine. Then after that, 18 Lenoir, I don't know exactly the name, but he started. He came up with the first commercially successful internal combustion engine. Before that, almost everything was the external combustion engine. We have already discussed about this an external combustion engine. So he came up with the internal combustion engine. So what is the difference? We know the difference, but why internal combustions are important? Because internal combustion engines reduces the size manifold. External combustion engines requires places where it need to where a combustion or the generation of the heat is happening somewhere. It is to be transferred to somewhere in some other means. Another medium may be used like steam to create steam, like water. A boiler is required there. Then if a space for engine is required, too many components will be coming in that, and it will be immensely large. So coming to the internal combustion engine, it would be very small. So that is the difference. Okay. So it's very important to have a internal combustion engine. So this is another milestone here. So and in 1861, Nicholas Otto, he came with the first internal combustion two-stroke engine. You have heard about the two-stroke engines. You may be having a much good idea about the two-stroke engines, because many bikes, as you know, is roaring on Indian roads as well as many other roads with high powers. which is made of two-stroke engines. So again, the Nicholas I mean, this was a petrol engine. Okay, two-stroke petrol engine. So petrol engine works on the principle of Otto cycle. I hope you understood how the name Otto cycle came, because this was the inventor. Otto was the inventor, so we call it as a Otto cycle, where the two petrol engines works. And in 1861, he invented the two-stroke internal combustion engine, and in 1877, he came out with the four-stroke petrol engine. That also works on the basic working cycle of Otto. Another invention was in 1883, a six-stroke engine was introduced, but it didn't went that that level. But still, people are trying to create six-stroke engines, especially for the diesel cycle. That we will discuss later. So, Charles Parsons, Charles A. Parsons in 1884 came up with the steam turbine. Steam turbine, you know, I hope almost everyone knows what is a steam turbine, which is run by steam to create a mechanical energy. Usually it is used in electrical production. The heat is converted to mechanical energy by the steam turbine, and that is coupled to a generator that will generate electricity. Okay, usually I'm not telling this can be used in any way, because it's giving a mechanical output that you can convert to whatever you want. So usually it is being used in electrical systems. So then in 1892, one of the major milestones where Rudolf Diesel came with the diesel engine. He patented the diesel engine, which is another milestone uh, in the evolution of heat engines. So these all things happened in 19th century. And 20th century also, there are many other further developments like rocket engine, liquid rock fuel engines, rocket engines were developed. Tesla came up with the Tesla turbine. Gas turbine was before this one. Gas turbine was just on papers. Just working models were there. This was first running model, commercially available model. So again, Wankel engine in 1996, similar to Wankel engine. Wankel engine is a rotary engine, similar to our two-stroke, four-stroke petrol engine, but it is a rotary engine. It's somewhat like a rotary plus reciprocating engine. That's used in racing cars and all. It has it runs at a very high speeds. It's capable of running at very high speeds. Wankel engine is capable of running at very high speeds, but have a defect that it can't run slow. I mean, like conventional reciprocating engines. So we'll discuss that also later. So this is not a common in on commercial cars and all. So in 20th century, that is these times, whatever happening is very micro scale. A lot of researches are going on actually, but not great ones, other than the listed ones, that micro or nano scale engines are being developed nowadays. For we know nano robotics and is all coming. So many developments are actually happening. So we are not going to discuss these much things. It's just you want to know. I just wanted you to know a lot of things are happening. Still, you know, right? Many advancements that is being listed by the manufacturers of many vehicles in the engines. They are claiming a lot of advances. So we will move on to the basic laws of thermodynamics. So zeroth law is the first one that we are going to discuss. This is of very little importance. I mean, it has importance, but it's of very little importance when we are going to study about the heat engines. But as I want to mention the first law and second law, I just also want to mention the zeroth law. That's why I put it in the slides. So so it states that if you take three bodies, that is body A, body B, and body C. If body A is in thermal equilibrium with body B, and body A is in thermal equilibrium with the body C, that is is in thermal equilibrium with B, and A is also in thermal equilibrium with C, then the bodies B and C are also in thermal equilibrium. It is it's not a big deal that you can understand, right? That is, for example, if you measure your temperature, if you don't have fever, it will be showing 32, right? 32, I guess, 30 degrees Celsius. 32 or 34, 32, I guess, 32 degrees Celsius. And if you are going to measure the temperature of your friend nearby, is also having the thermometer is also showing the same temperature, and the third person is also having the same temperature. I mean, the third friend, your third friend is also having the same temperature, showing the same temperature. Then all three are in thermal equilibrium, right? You all having the same temperature. That is what is being mentioned here. So it is a basic law which give birth to the measurement of temperature. Okay, it gives the measurement of temperature. That is, for example, how Celsius scale is defined is that it has a zero value, right? So what is the freezing point of ice? Freezing point of ice is 0 degrees Celsius, right? And the boiling point of water, same thing, converted to liquid and again boiled. That temperature is taken as 100 degrees Celsius. So 0 degrees Celsius, 100 degrees Celsius. So it is set as 0. Whatever the if you take a thermometer and put it in the ice, the height of the mercury column shown is marked as 0. Actually, it's not a thing that is being gifted by the god, but we created this mercury. This mercury thermometer, right? So we kept it here and marked whatever height is being shown in this thermometer when it is kept in the ice, and marked it as 0. And again we put it in the boiling water, and we whatever the height that is being the height rise of the mercury that is being shown in the thermometer is marked as 100. So 0 and 100, right? Those thermometer that scale, that is difference in height, can be divided into 100 parts, and each unit will be given as a 1 degree, right? That's how it is happening. So if you are measuring so any temperature in between this one, okay, 0 and 100, if a body is placed here, I would say 32 degrees our body temperature, and another body which is placed here. So when the thermometer is considered as a second body, and the body placed here is considered to be A, the body, the thermometer placed here is considered to be body B, and when this body comes in contact with this body, there is some process that is happening, right? The mercury level will rise up, and when will it stop? When it stop, it will stops when when it is showing the temperature of this body, or we can say these two bodies begin thermal equilibrium. This mercury in this thermometer and the temperature of the body, whatever body is being placed at 32 degrees Celsius, came into thermal equilibrium and is showing the same temperature. When I'm keeping this thermometer in a body of a person who is having 32 degrees Celsius, the same this thermometer will show the same height. That means that body, the person's body, and the mercury in this thermometer came into the thermal equilibrium. So these three bodies came into the thermal equilibrium. Initially, that's what the law is stating. That is, if body A and B are in thermal equilibrium, if the A and C is also in thermal equilibrium, then B and C are in thermal equilibrium. That means the body here and the body of the person here are in thermal equilibrium. Simple as that. Okay. So next we will go to the first law of thermodynamics. First law of thermodynamics is a very important law coming to the when we are going to discuss about the hold on a second. Okay. So first law of thermodynamics is very important when we are considering the heat engine, working of a heat engine. So what is a first law of thermodynamics? Similar to that of the second law of Newton's second law. Newton's second law of motion. What is it state? It states the conservation of energy, right? Law of conservation energy. That means energy cannot be created nor be destroyed, but it can be converted from one form to another. Whatever the energy be, it cannot be destroyed, but can be. We also can at the same time we can also we cannot create also. We cannot create or destroy any form of energy, but it can be converted to other form of energy. Okay. You can't hear? Hello?
Yes, we can
Hello?
hear.
Yes.
I think Shanish, I think you have to check your microphone. So, so that's what the first law states, but in a different way. As I said, what all are the energy in transient in thermodynamics? It's the work and heat, right? So that terms will be we will be taking here for a closed system. For closed system means that is operating within system. Then closed system means there is the systems or the body where there is no mass transfer across the boundary of the system. That means if you take a closed jar containing hot water, a closed container that is carrying hot water, their mass won't be coming out of the system, right? The steam won't go out of the system, but what happens? It gives out the heat. The hot water will be giving out the heat across the boundary of that jar. That is considered to be a closed system. You can see water that is being in the walls on the container lid and all, right? When you are when you are taking a closed container, when you open that after some time, you can see water droplets over that cap. That's because the mass trying to escape from that system or the jar, but what is happening that the wall container, I mean the container of the jar, I mean the walls of the jar helps in transferring the energy out of the jar, but not the mass. Mass is not transferred. At the same time, energy is transferred. That kind of systems are called the closed system. I'm not going too much into the thermodynamics because it will it itself is a subject. So I'm not going to discuss too much of that. But these kind of terms I will explain in between. So closed system is a system or a body that won't permit mass to cross across the boundary of the system. It retains within mass. Mass means what is mass? It's the molecules or maybe the matter within that the working fluid. Hold on a second, please. Sorry for the disturbance. So we were discussing about the closed system. Okay, closed systems are systems which won't allow the mass to cross across that system, but it allows the transfer of energy. Whatever be the energy, it will allow to cross the boundary. As I said, the hot water, the jar containing a hot water, which is closed jar, which is containing a hot water. It allows the heat to transfer across the system, cooling the water inside. But at the same time, mass is not crossed across the walls of that jar. Okay. So in such a system, for example, we can say heat engine also. I mean, internal combustion engines also. Sorry. I'm sorry about that. So you can consider that. Sorry about that. So whatever the system which is operating in a cycle, cycle, I told you what is a cycle. That is continuously producing work output, or the it is not a cracker that goes up. It will continuously produce a work in a cycle. It will operate in a cycle. That kind of a closed system, the net work done is equal to the net heat transfer. Okay, you are getting the point. Like in a closed system, operating in a cycle, that is operating continuously, which converts heat into work. In that system, in a cycle, within a cycle, the net work transfer is equal to the net heat transfer. Or we can say the net heat transfer is equal to the net work transfer. That is, we already learned the law of conservation of energy. What does it say? Energy cannot be destroyed nor be created, right? So whatever the heat supplied to that heat engine or that body, it is not going to fade away. I mean, it is not going to be destroyed, right? It will be converted to some other form, or it may stay as heat itself. So the mass, the heat, if we are giving some heat to the system, if we are giving some heat to the heat engine, that heat, for example, okay, I will representation not here. What just imagine a heat engine where we are giving some heat into the system. We are giving some heat into that heat engine, where a part of that is being converted to the work. Remaining stays as heat itself, right? A heat is being supplied to a heat engine, a part is being converted to work, mechanical work, and the remaining stays as heat itself. So what is the total conversion of heat? It is the heat supplied minus the heat rejected by the heat engine, right? Heat supplied minus heat rejected is the not net heat transfer. And what is the work transfer? This difference is the work transfer. Whatever the difference, whatever the heat converted to work, whatever the part of the heat converted to work will be we will be getting that by reducing, by subtracting the heat supplied minus the heat rejected. That is what is being mentioned here. That means you have to clearly understand that it happens in a closed system which is operating in a cycle. Okay, it's a closed system, or we can call it as a heat engine which is operating in a cycle. The net heat transfer is equal to net work transfer. So so it's also known as the law of nature. Then it's represented here, that is a net heat transfer, that is heat supplied minus heat rejected, is equal to the, if some kind of work is being rejected, or work, sometimes work can be rejected also. For example, frictional forces, whatever heat work being created, that will be reduced by the frictional forces. What is happening is also the mechanical energy that is being reduced from that. So we can also say that the heat supplied minus heat rejected, which is equal to net work produced minus work loss. That also can be written like that. Or we can say net heat transfer is equal to net work transfer. Simply as that. Okay. So in a process also there is something, or we can say if it is not a cyclic process. cyclic process, I said that like it will be operating in a cycle, that the process continues as a cycle. If it is not a cycle, what will happen is that if it is not a high cyclic process, that is or process happening, that is heat is transferred and a work is produced, but it is not being not coming back to the initial state. For example, the crackers, or maybe a gunshot, I mean the bullet. But there what happens is that there is a heat transfer, of course there is a work transfer, and the difference will be the change in stored energy or change in internal energy, or delta U. Okay, you are getting that this is a stored energy. Delta U is the stored energy. I told you initially stored the three type of energies are there. That is stored energy, energy in transit, that is heat and work. Here we are considering the mechanical work. So net heat transfer minus net work transfer will be stored as what change in internal energy. Change in internal energy may be increasing or it may be decreasing depending on the transfer. Okay, if the heat is more and the work is less, then the change in internal energy will be increasing. Plus, if the heat is being reduced or the work is converted to heat, in some other system it is like that. For example, heater and all, that is not a heat engine, it is considered as a heat pump or refrigerator. It is considered, we know, right, where we will be giving work and will be converted to heat. So in that system, internal energy will be reducing. Just saying this is not that important, but this is important. This thing is important, but this have a limitation. Actually, this law has a limitation. It's just saying that one energy can be converted to the energy another energy, but how much, that is not being defined here. Some form of energy can be completely converted to some other form. Some energy can only partially be converted to other form. For example, heat. Is there any engine? Have you seen any vehicle that is not being heated up with an engine? No, right? That is, whatever the heat energy given to that, only a portion can be converted to work. The remaining will be rejected to other parts of the body, or maybe rejected to the atmosphere, right? So the heat cannot be completely converted to work. That is not stated by the first law of thermodynamics, but is stated by the second law of thermodynamics. Because before going to that, I was just mentioning about that. So so this is the first law of thermodynamics. It's very similar to law of conservation of energy. So next one is a perpetual motion machine, or PPM1. Sorry, PMM1, perpetual motion machine of kind 1. It is a it's an engine, imaginary engine, which opposes the first law. It's only an imaginary engine which opposes the first law of thermodynamics. What it does is that without a heat input, it will produce work continuously. That means what it does is that it opposes the law of conservation of energy. We know we cannot create any form of energy with nothing, or we cannot, as the statement says, we cannot create the energy, right? This engine, what happens is that it will create work without nothing, no heat input is there. Or in the converse, in the other way, it will produce, it will take all the work without producing heat. So these are concepts used to study a heat engine in some other levels. So just to know what is a PMM1 and PMM2, that will come. What is a PMM1 and its converse? PMM1 and its converse, both the engines are imaginary engines only, which opposes the law of conservation of energy. It's an imaginary engine which produces work or it consumes. And here what is happening is that it creates work, or it creates a new energy. Here what is happening is that it destroys energy, right? It is consuming work continuously, but is not converting to any other form, or it is not giving out as heat or any other forms. It's consuming work or create. It is destroying. Here it is destroying energy, and here it is creating energy. Hope you understood. So, what is the time? Now, oh, 10 minutes is there. So we will move to the second law of thermodynamics. We'll move to the second law of thermodynamics. Before that, I have given a problem, or we will do this one. Okay. So this is a closed system where which is producing a series of energy transfers are being happening. It is also happening in a cycle. You can see a process A to B is happening, B to C is happening, C to D is happening, D to E is happening, again E to A is happening. That means the system again comes back to the initial state, that is A. Initially it started from A, it ends in A. That means this process is happening in a cyclic process, and in each process the work input or the or output is given, heat input or output is given. So here we can see in A, B there is no work input or output, but heat input is there. How so one more thing you have to identify understand is that when we are supplying heat into that engine, it will be taken as positive. When we are giving heat into a system or an engine, we will consider it as positive. Okay, so positive means it's giving heat input. In converse, work will be what is being given out. The positive work is what is being given out. That is in an engine, what we want actually. Heat should be fuel. The burn fuel will be converted to will be creating some heat energy, and that heat energy, that is a supply of heat energy, that should be converted to work, right? The supply of heat energy should be converted to work. That is the positive way what we want. That is positive output, the what we want. So those two things, the supply of heat energy and taking out of the work, or if the engine is giving out the work, both these cases are considered as positive. Okay, I hope you are understanding. So this will be positive, this is positive, and we can consider is this one as what this can be considered as heat input. Okay, so in this AB there is no work output input. So in BC, on BC what is happening is minus 200. That means it's a work input or output. So minus, since it is minus, what we want is a work output, right? Since it is a minus, then we can say that is a work input in that process. In that device we are giving work input, not output. The system is not giving out the work, but we are giving into the engine or into the device, whatever be it may be a heat engine. It's not mentioned there, it's a common rule. So in the whatever be the device, it is taking a heat work input. Minus means work input only, it is taking a work input. Similarly, in the same process there is a heat output. This is a lost, right? It's not being converted to work. This part of heat is not converted to work. That's why, that means it's given a negative sign because it's a heat output. So here it's a plus means work in output, and 0 no heat transfer. Here minus 540, that is again a work input. Here is no heat input or output. Here also there is no heat input or output. So we have to find the work transfer here. It may be plus, it may be minus. If it is plus, it will be output. If it is a minus, it will be a work input. So solution is very simple. There are many other problems also, which includes some thermodynamic equations will be coming, basic equations only, but I just want to go through the basics, very basics. So I'm not going to take bigger problems, only very small problem. Here, here is a solution actually. So what I have done is that this is a cyclic process. So I will be taking the total sum of the work inputs. So the net work done, it may be plus or minus, right? It will be 3 minus 350. The sum is minus 350. Yes, minus 350 plus this value. This question mark is taken as W in EA. The process, in this process, EA process, we'll be taking it as work W. So minus 350 plus W will be the net work output, and net heat transfer will be the sum of this one, that is 100 50 plus 50 minus 150, that will be 100. So as per the law of first law of thermodynamics, the net work done will be equal to net heat transfer, that is minus 350 plus W will be equal to minus 100. So will be so that means heat transfer minus work transfer is equal to 0. That is this equation, heat transfer minus work transfer is equal to 0. That is 2 minus 1 is equal to 0. Equation 2 minus 1 is equal to 0. That is 100 minus 100 minus 350 plus W is equal to 0. So the minus is there. So it will be 250 minus W equal to 0, or work will be equal to 250 kilojoule. That is a work output. Here EA, it is a work output. How it is considered as output? Because it is a positive sign. So work output will be positive. So we'll be discussing the second law of thermodynamics in next class. It's almost up to time. Hope you understood what we have learned today. Any example for PMM1? Actually, I told you it's an imaginary. There is no such system actually. Okay, it's an imaginary one, just to study about the heat engines, and it's not a real thing. So it is called as PMM1. Okay, PDF notes are good. I will provide. What is the relationship between mass and heat engine? Yeah, of course there is a relationship between mass and heat engine, right? Heat engines are of different types actually. For a very example, you have a petrol vehicle, right? If you can just consider. Okay, solution. So you didn't understand the solution? Okay, I will explain again, 1 second. So what we're talking about, mass and heat engine. So will your vehicle run without petrol? It won't run, right? So we need a continuous flow of petrol which carries chemical energy, which is burned into thermal energy, or the heat energy. So of course there is relationship between mass and energy produced, that heat engine. Of course it is there. So if you are asking about the first law of thermodynamics, here that's what I was telling, that it's relating energy only. It is a relationship between energies only, and if it is an open system, as I told, open system also, there is first law will be applied there. That is the steady flow energy equation is there actually, that we are going to note. It's also important in heat engine, but it requires a lot of other knowledge within the thermodynamic system. So I didn't took that, but for understanding purpose only, I was telling this first law of thermodynamics. Actually, we all know mass will be carrying energy. So the flow of energy will be associated with the mass flow also. That means, and as I told, energy is there within. For example, the working fluid is steam in a steam turbine, right? I also explained about the steam locomotive here. Here, what is carrying the energy? Heat energy is being carried uh, by the steam here, right? You can see the steam is carrying the heat energy that is being supplied. So this is a mass that is being carrying the energy. So it is important. That's an open system actually. And one more question was there. I couldn't see about the problem. Okay, simple as that. What is the first law of thermodynamics? First law of thermodynamics says that in a hello. So first law of thermodynamics says that in a closed system operating in a cycle will the net heat transfer is equal to the net work transfer. So this process, this is a cyclic process. We understood this is a problem actually where a number of processes were given. In each process, the work output or input is given. Also, heat output or heat input is given. Okay, so we are going to check whether it's a cyclic process. So A to B, it's a process. B to C is there. C to D is there. D to E is there. E to A is there. That means the system returned to the initial state A, right? The started frame A, ended in A. Again, the same process happening. So it is a cyclic process. So in the process AB, in this system, we can apply the first law of thermodynamics in a closed system. It's a closed cycle, right? So it's closed system operating in a cycle. I mean, in a cycle, it's a cyclic process. So we can apply in the first law of thermodynamics here. So we will find the net work transfer. This is the, if you take the sum of these work, it will be the net work transfer, right? So minus and plus are given here. Minus means it's the work output. Work input from an engine or for any device, whatever we expecting, what we are useful, whatever it is being useful to us is the work output. Actually, mechanical work output is a useful thing for us. So if a device is giving work output, we will consider it as a positive. That means this one, this 300 plus 300 is a work output. Both the other things are negative. That means work is given into the system, some way that we are giving some pushing, or maybe some kind of energy is given to the system as a work into the system, that minus 200 and minus 450. If you are given taking the sum of this one, what will be the 200 plus minus 200 plus 300? It will be 100 minus 450 will be minus 350. That is being listed here, minus 350. Network done is equal to minus 350. And also in this system, EA, in this process, EA, where I have given a question mark, the work there is to be found out actually. Work, whatever be the work here is to be found out. I hope you can see what I'm showing here. Here, what you, so I am taking it as W. This question mark I am taking as W. So the sum here, work, sum of the work here is taken as minus 100, sorry, minus 350, right? Minus 200 plus 300 minus 450 will be minus 350. And the work here is the W. So my net work done will be the minus 350 plus W, right? Now we are going to find the net heat transfer actually. Net heat transfer is will be the sum of these two values, right? There is no other heat transfer here, all are zero. So in a process A, B and B, C only, there are two heat transfers. We are going to take the sum. So the net heat transfer is equal to minus 150. Minus indicates, in a system, minus indicates, I mean, regarding the heat transfer, minus indicates the heat is taken out of the system, or the engine is giving out the heat or rejecting the heat. Minus means rejection of heat. Plus means heat input. We in an engine or whatever we want in a system is that heat is to be given and work is to be taken out. So the required things are taken as positive. So plus 50 means it's the heat input, and minus 150 means it is a heat rejected. So the total heat transfer will be the sum of these things, 50 minus 150, that is minus 100. If you add these two, it will be the minus 100. That is given here. Net heat transfer is equal to minus 100. So we are going to apply the first law of thermodynamics. That is, the first one will be equal to, or the equation one, we have marked 1 and 2. This will be equal to this one, or 1 will be equal to 2, or we can 1 will be equal to 2 means what? 2 minus 1 will be equal to 0. right? If 1 is equal to 2, this equation is equal to 2, that means 1 minus 2 will be equal to 0. Of course, it will be equal to 0. If 2 terms are equal, then the one term minus the other term will be, of course, is equal to 0. That is being written here. That is net heat transfer minus net work transfer is equal to 0. We are applying these values, that is minus 100 minus this value, minus 350 plus W is equal to 0, and 250 will be is equal to W. That is the work, whatever, and the work will be equal to 250. And taking the W to the other side, that is W is equal to 250 kilojoules. That means it is positive. That means what? It is a work output. Okay, hope you understood. Where is the messages? Hope you understood. I don't have the name. Okay. Thank you. Don't please, if you understood and you are interested in this one, please don't skip the next class. Thank you.
Okay, sir. Thank you.
Equation 2 minus equation 1, not 2 minus 1. Okay, thank you. Good night. Bye. Bye.